Hi there. In this video, we're going to be talking about AP Chemistry's topic 4.7, types of chemical reactions. And on the AP test, they're going to be looking at three different types of reactions, and they'll specify in the problem that they're asking you for one of these three types of reactions. And the three types of reactions they're going to look at are redox reactions, which we'll talk about in just a second, acid-base reactions, and the third type is precipitation reactions. So these are the three categories that they're going to talk about. And in first year chemistry, you learned about five types of reactions: synthesis, decomposition, single replacement, double replacement, and combustion. But those fit under these types of reactions. And so these are organized a little bit differently, but they still are going to hit on the types of reactions you're familiar with. You're just going to have to know which of these three those types of reactions fall under. So the first type I want to talk about is the most varied of these three, and that's redox. In a redox reaction, you always have the reduction and oxidation of an element. So this means that you have oxidation, which is the loss of electrons, and you also have reduction, which is an element that gains either one or more electron. The way you can remember these two things, again, is oil rig. Gotta say it like a Texan. Oxidation is loss of electrons, reduction is gain of electrons. So in a redox reaction, you always have this happen. One element will gain electrons, one element will lose electrons, and that's how you can recognize these. Redox reactions include single replacement reactions. Single replacement reactions are always redox. Combustion reactions are always redox. Synthesis reactions are always redox, and decomposition are always redox. So how do you know that a redox reaction has taken place? Well, let's just look real quickly at a reaction. Let's say that you had some copper and you reacted it with some silver nitrate, and you produced silver and copper nitrate. So if you look at this reaction, and actually I'm going to complicate it a little. Let's change the charges here. If we look at the charges in all the reactions, on all the elements in polyatomic ions, you'll see that there's a change. Elements that are by themselves always have a charge of 0, an oxidation number of 0. So copper has an oxidation number of 0 here. If we go look on the other side at what it's bonded to, nitrate is -1 and it's bonded to 2 nitrates, so now copper is 2 positive. Because copper went from 0 charge to 2 positive charge, that means that copper lost 2 electrons. Copper lost 2 electrons, and oxidation is lost. So copper got oxidized, it lost electrons. If one element loses electrons, then the element has to gain electrons. And so if we look at silver here, silver is 1 positive when it's bonded to nitrate, because nitrate is 1 negative. When an element's by itself in its elemental state, it always has an oxidation number of 0. So silver went from 1 positive to 0 charge, meaning it had to gain an electron in order to go from a positive charge to a neutral charge. It gained 1 electron. So silver was reduced in this particular reaction. And again, the term reduced means the charge was reduced. It gained an electron, but the charge was reduced in that process. So you'll notice that in this single replacement reaction, we had an element by itself that became bonded in a compound. It must have changed its charge in order to do that. Same thing with another element that was in a compound and it went by itself. Now it has to have changed its charge in order to do that. So single replacement reactions are always redox reactions. Combustion is always redox. Synthesis and decomposition, always redox. So just a reminder on how you determine oxidation numbers on compounds. There's a few rules, and I'm going to kind of simplify them here just to make it go fast. But if you remember these rules for determining oxidation numbers, you'll go well. Remember, pure elements, an element that's just by itself, oxidation number is 0, always. If you have an element in an ionic bond, the oxidation number equals its charge. So whatever, like we did up here, we figured out the charge of the elements in this. So we figured out the oxidation number of the silver by being bonded to the nitrate ion. So oxidation numbers in compounds are just the charge of the ions in the compounds. F is always -1. You can count on that because it's the most electronegative element. It always gains 1 electron in compounds. If it's by itself, of course, if it's F2, then it's neutral, because then it would follow the first rule. Pure elements have a charge of 0. Hydrogen is almost always +1. The exception is in when it's bonded to metals. If they're bonded to metals, then you have a hydride and it has a -1 charge, but almost always. Oxygen is almost always -2. The exception would be with peroxide, and peroxide is O2 2 negative, where each oxygen has a 1 negative charge, but that's very rare. Chlorine, bromine, and iodine are always -1, except, and this is important, when bonded to oxygen or fluorine. So if you have chlorate, chlorite, hypochlorite, then the chlorine's going to have a positive charge. Bromate, bromite, hyperbromite, same thing with iodine. If they're bonded to oxygen, then they're going to have different positive charges because they're bonded to oxygen, which is always -2. So they're a little tricky, but normally they're -1, except in those polyatomic ions. So that's how you determine oxidation numbers. Let's just look at an example of this. Let's say that you had methane and you wanted to figure out the oxidation number on carbon. Well, following these rules, hydrogen is +1, so hydrogen's +1, and there's 4 of them, so 4 times +1 is 4 positive. So what is carbon's oxidation number here? Well, the compound has to be neutral because it's a compound, and so its oxidation number must be 4 negative to cancel out the 4 positives of hydrogen. What about in carbon dioxide? Let's look at carbon dioxide. In carbon dioxide, oxygen is -2 because oxygen's almost always -2. So if we have 2 atoms, each with 2 negative charge, that makes carbon 4 positive in this particular case. So carbon is 4 positive. Let's look at another example. Let's look at ethine, which is C2H2. So in this case, hydrogen is almost always +1, as it says right up here, +1. So 2 hydrogens, each with a +1 charge, that gives us a total of 2 positive charge total. So what cancels out 2 positive? 2 negative. There's 2 carbon atoms here, so they split this 2 negative charge, so each carbon atom is 1 negative. You'll notice carbon does a lot of weird stuff in these organic compounds, but looking at hydrogen with its 1 positive charge helps us figure that out. I do want to just insert here a quick practice with oxidation numbers of polyatomic ions so that you can see how that works. Let's say that we have the nitrate ion, and nitrate has a 1 negative charge. So what is the oxidation number on the 2 elements? Well, oxygen's always 2 negative, and we have 3 oxygens, so times 3 gives us a total of 6 negative charge. So the overall charge on this polyatomic ion is negative. So what plus a 6 negative would give us an overall negative? And the answer is 5 positive. 5 positive plus 6 negative will give us an overall negative. That means that the nitrogen is 5 positive charge. So that gives you the oxidation number there. Let's look at one more. Let's look at ClO2 with its negative charge. Oxygen is always 2 negative, and there's 2 of them. So the total negative charge here is 4 negative. The overall polyatomic ion is negative, so what plus 4 negative would give us that overall negative charge? 3 positive. So chlorine, in this particular case, has an oxidation number of 3 positive. Remember, oxidation numbers are just a way of kind of accounting for electron density. They don't tell you actual charges of these things. They just tell you kind of where the electron density lies. And in this case, the electron density lies very much on the oxygens and not on the chlorine. So just wanted to give you a quick reminder about how to do polyatomic ions. Now back to the regular video. Okay, so let's go on to our next topic, which is acid-base reactions. So we've talked about acid-base reactions quite a bit recently, but just a reminder, in an acid-base reaction, there's a transfer of protons, either one or more protons. Acids donate protons, and bases accept protons. Okay, I am not going to do some practice here just because we've talked about them a lot, but acid-base reactions transfer protons. Actually, let's do one quick one real quick. Let's say we have the carbonate ion, which is HCO3 negative, and we react it with ammonia. And so in this reaction, you'll end up with CO3 2 negative and NH4 positive. What was the acid in this particular reaction? Notice these both have hydrogens. So what was the acid? Well, the acid's the substance that gave away a hydrogen. HCO3 became CO3. So this was our acid. That means this must have been our base. And if you look, it went from NH3 to NH4 positive. So that is indeed our base. And then over on this side, what are these going to be called? Well, our acid has a conjugate pair. It became what's called the conjugate base. And the conjugate base is the substance that had lost the hydrogen from the reactant side. So that's our conjugate base. Why is it called a base now? Well, because if we ran this reaction the other way, it would gain a hydrogen from the other substance. The base has a conjugate pair, which is the conjugate acid. So the acid and the conjugate base are a conjugate pair, and the base and the conjugate acid are a conjugate pair. The base becomes the conjugate acid becomes the conjugate base. Our third type of reaction, which I know you're very familiar with, is precipitation reactions. And in precipitation reaction, you have two soluble substances or aqueous substances form a precipitate, an insoluble substance. So soluble substances form a precipitate in a double replacement reaction. And so in these types of reactions, you do need to be really familiar with the soluble compounds that you know are always soluble, and that is, always soluble. Na positive, K positive, NH4 positive, and NO3 negative. These always form soluble compounds. So you just need to keep in mind that if you see one of these, you know that it forms a soluble compound, so the other compound must be insoluble if it's a precipitate reaction. And again, these are double replacement reactions that do precipitate reactions. So that's just a quick refresher about the types of reactions. If you have any questions, of course, please talk to me. I'll be happy to talk to you about any of these because this was really fast.